Assalamualaikum warahmatullahi wabarakatuh. We are from Group 7 and we will be presenting about our project, which is RFID Door Lock System. So without further ado, let's move to introduction. So what is RFID? So RFID is a technology that enables wireless data transmission. So it consists of tags and radio transponder for radio frequency and readers of radio frequency tags. So the objectives for this project is to produce more efficient way for door locking system. Next, to produce mathematical modeling of RFID system and validate the calculation by using Matlab software. Finally, to create a stable system by introducing PID into the system. Next, we will move on to the literature review for this project.
Assalamualaikum warahmatullahi wabarakatuh. My name is Madya Ts and I will present to you the literature review of our project. So before we talk more about our project, which is RFID Door Lock, we will need to see what is the difference between our project and the existing conventional automated door lock. Okay, so first of all, the conventional automated door lock also use an RFID and Arduino Uno as the controller and the sensor. And then, as we all know, RFID is widely used in the world for various applications. For example, in Malaysia, the newest application of RFID is the toll that is used now, and it is still in the test phase. Okay, so what is the difference between the conventional automated door lock and our project with RFID door lock is that the conventional automated door lock does not have a feedback system, and it is fully controlled by Arduino Uno. What is meant by that, it will be explained more in this presentation. Okay, so this is an example of a conventional automated door lock. So as you can see at the left picture, it is a RFID module, which is also the sensor, and the card itself, which is touched on the sensor. And then, as you can see, the deadbolt is attached to a DC motor, and when it is touched, it will unlock or lock without any feedback system. Okay, so the next thing I will tell you is the list of component and the function of the component. Okay, there are a total of 6 components that are used in our project. So first of all is Arduino Uno. It is our controller for this project. And then stepper motor with driver, which is the actuator, RFID module, which is the sensor, wire to connect all the components together, micro push button as our feedback system, and the power supply. It is to supply power so that our circuit is functional. Okay, so all the components are arranged as this design, which is the circuit design that we created. Okay, so as you can see, RFID module, the Arduino Uno, and the motor itself. Okay, so let's go to the block diagram of RFID door lock system. Okay, so let me explain it briefly about the block diagram. Okay, first of all, we can see that there's a sensor of which is RFID module, and when the sensor detects a signal, it will see the micro push button. If it is pushed, it means the door unlock, and when it is not pushed, it means the door unlock. So if it detects the micro push button is pushed, then the control device, which is Arduino Uno, will send the signal to actuator to unlock the door. Okay, so that's how a simple explanation of our block diagram. Okay, so that's all for the literature review. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and a very good evening. My name is Muhammad Badrul-Aisham Bin MD Zain and my metric number is DD180032. So for my part, I'm going to talk about mathematical modeling by subsystem. So in our project, there are 2 main subsystems. So the first one we have electrical subsystem, and the last one we have mechanical subsystem. So in electrical subsystem, we have power supply, resistor, inductor, and also electromagnetic field. So from four of the component, we're going to simplify it into one equation. So in mechanical subsystem, we have rod and pinion, stepper motor, and also micro push button. So the same thing we do in electrical subsystem, we're going to simplify it into one equation. So from both of the equation we obtain from the electrical and also mechanical subsystem, we're going to substitute it and also Laplace transform it, and then we will get the final equation of the transfer function. So as you can see from the equation above, that is the final equation of the transfer function after we Laplace transform it. And then after that we're going to insert the unknown with the value that we got from the journal that we searched from the internet. So after that, after we insert, we're going to calculate it manually, and then we will get the final transfer function. So for time response analysis, there are two, which is open loop and closed loop. So in open loop, as you know, there is no feedback. So as you can see from the figure below, that is the block diagram for the open loop. So after we insert the transfer function into the Simulink, the Simulink will generate a graph, as you can see from the figure on the right. So the next one is closed loop. So closed loop, as you know, closed loop has a feedback. So for our project, our feedback is 1, or we could also call it as unity feedback. So as you can see from the figure below, that is the diagram for closed loop. So after we insert the transfer function into the Simulink will generate the graph, as you can see from the figure on the right. To eliminate the unity feedback, we're going to use the formula of GS divided by 1 plus GS times 1. So by manually calculating it, we're going to obtain the transfer function for the closed loop system, which is, as you can see from the equation below. That's all from me. Thank you.
Assalamualaikum, my name is Muhammad Hafiz Albar and I will discuss about the closed loop graph characteristics. So as discussed by Eric just now, from the closed loop transfer function we will be able to produce a step response graph. So in the step response graph we consist of a few specific points, which is the rise time, the peak time, the delay time, and the settling time. So let's look at the definition of all this first. The rise time is the time required for the response to rise from 0 to 100% of its final value. The peak time is the time required to reach its first peak by the overshoot. And delay time is the time required for the response to reach half the final value the very first time. And finally, the settling time is the time required for the response to reach steady state. So from the graph, we can determine the value of delay time, the peak time, and the settling time. So here we can predict the value, such as the delay time is 1 second, the rise time is around 1.2 second, peak time is around 1.4 second, and settling time is around 2.3 second. However, if we plot it manually like this, the value might not be accurate. So in order to improve the accuracy of the value, we can obtain it from the Matlab software. So here is the coding script that will be applied in Matlab. So over here we can see that num and den, which is represent the numerator and denominator of the transfer function without the S domain. So as we insert the coding script, this will be pop out in the command window. So from here we will obtain the result of the desired rise time, delay time, and more. So here is the result. We can see that the rise time is actually 0.121 second, peak time is 0.33 second, and settling time is 0.986 second. So that's all for the step response graph characteristic.
Okay, now My name is Wan Muhammad Haikal bin Wan Huzanizam. So we will proceed to the root locus subchapter. Okay, before we start, what is root locus actually? What is the use of root locus in our control system? Okay, so root locus is this technique used as a stability criterion on the field of classical control, theory developed by Walter R. Even, which can determine the stability of the system. Okay, so when we produce or when we create a root locus based on our transfer function, we can observe the stability of our system by looking at the plot of root locus. Okay, basically when our root locus are located at the right hand side of the S-plane, we will consider as the system is not stable. And if the plot of root locus are located on the left hand side of the S-plane, so we will call as our system stable. Okay, so the root locus plot the poles of the closed loop transfer function in complex S-plane as a function of a gain parameter. So for root locus, we only focus to determine the stability of our system from the transfer function. We only observe the denominator, which also called as poles of the transfer function. Okay, so proceed. Okay, so here step to perform root locus is, first we need to identify the denominator of transfer function that we made in the previous section. So the transfer function, which is the relationship between the output and the input, which is displacement and voltage for our system, is as stated above. Okay, so we will only look to determine the stability of the transfer function. We focus on the denominator of our transfer function, which is also called as poles, and to change it into the characteristic of root locus, we will take the denominator and equal to the value of 0. Okay, so next, after that, we need to identify all the roots for the numerator and the denominator, which here we have 4 roots for the zeros or numerator and 5 roots for the denominator or poles. Okay, as we can see here, the largest order for the numerator is 4 and the largest order for the denominator is 5. Okay, we can straight away identify the number of roots by looking at the order for the numerator and the denominator. So if the highest order is 4, so we will know that the equation will have 4 roots. But while for the numerator, the denominator, the highest order will be 5, is 5. So we will know that the number of roots containing on the denominator will have 5 roots. Okay, so as you can see, we have 2 type of roots, which is the real roots, okay, and another one is the imaginary roots. We can call our transfer function as complex equation because we have imaginary roots for our equation. Okay, next, in order to draw the root locus, we need to determine the asymptotes, which also called as the centroid for our root locus. Okay, and the formula for asymptote is the sum of poles minus the sum of 0 over n subtract by m, where n here is the number, okay, the number of poles, and m is the number of 0. Okay, so we need to be careful here because the sum of pole is the sum of the pole. Okay, while n here is the number of pole, which is 4, the number of 0, the number of pole, which is 5, 1 2 3 4 5, while for the sum we will need to add all this value into the sum of pole. Okay, so we get the asymptote at negative 992.73 which is the coordinate of pole on the real axis, on the x-plane, on the s-plane. Okay, so if you look at this coordinate, we know that the plot that we need to put in the real axis is equal to 992.73, which is located on the left hand side, negative, and on the imaginary axis will be 0. Okay, so the asymptote will be located on the real axis. Okay, that's the fact that we need to know from the asymptote's coordinate. Okay, next, after we find out the asymptote, we need to determine the angle of asymptote by using this formula, which is 2k plus 1 over n minus m, where n is the number of pole and m is the number of 0, and multiply by 180 degree. Okay, so k will be started from 0 until 4 until the maximum number of 0 actually. So before this, we know that the number of pole is 5, so we need to try until 5, until k equal to 4, because k equal to 0 also count as 1. So 1, 2, 3, 4, 5. So this is the angle of the asymptotes, the intercept with the asymptote, which is started by 180, 540, 180. We know that the root locus came out from the asymptote will be parallel to the real axis. Okay, so next, to find out whether our system is stable or not, we try to do the rule stability criterion by looking at the first column here to find out whether there is a change in sign. Okay, when there is a change of sign on the first column, we know that our system is not stable. Okay, so in order to generate a complex transfer function like this, it's easy to for us to use the Matlab software to generate the root locus graph for us. Okay, and the coding that we need to insert into the Matlab is stated below. So num is denoted as numerator and den is the denominator. So we need to insert the value of numerator and denominator without including the s domain in the transfer function. So like the numerator, we only write down the number, okay, the value without s. Okay, so this is the value for s4, s3, s2, s, and lastly the value without the s domain. Okay, next, for the denominator, as you can see, same as the numerator, we only include the number without putting down the s domain. Okay, so the command for the root locus will be rlocus, which is noted for root locus. Okay, then we gain our root locus graph like this. So as you can see, this is the condition of our system before we put the PID into our transfer function. Okay, PID is not present here, and we hope after we put the PID into the transfer function, it will change the root locus condition to stable, which is located at the left hand side of the s-plane. Okay, so basically this is the s-plane where the y-axis is the axis for imaginary and the x-axis is represent the real axis. Okay, so next we go to boat plot. Okay, what is boat plot actually? A boat plot is a useful tool that show the gain and phase response of a given LTI system for different frequency. Boat plot are generally used with the Fourier transform of a given system. Okay, so here are the 4 steps before we can draw a boat plot for our system. So first, we need to rewrite the transfer function in proper form. Okay, separate the transfer function into its constituent part. Okay, there is basically 5 main constituent part that we need to know. That is constant, the real zero, the real pole, the zero at origin, and lastly the pole at origin. That these 5 things we need to bear in mind when we want to draw the both plot, because we need to separate our transfer function into this constituent part. Okay, next, draw the both diagram for each part. First we need to draw for each part, and then we can proceed to the number 4 step, which is we draw the overall both diagram. Okay, so the overall both diagram will be a continuous line starting from 0 until infinity. Okay, so our transfer function is very complex, and it's hard for us to do it manually, so we just insert into the Matlab software to generate the graph for us by putting the num and then like root locus, but changing the command to boot. This is the only distinction between root locus and boot. Also for the Nyquist, plot later. So we change the command to boot, and then Matlab will generate the graph for us. So this is the graph for the magnitude, and this is the graph for the phase diagram, for the phase both diagram. Okay, the x-axis denoted as a frequency, and for both graph we know that y-axis is the magnitude, another one is the for phase. Okay, for magnitude, the slope we get here is equal to negative 20, because the trend is going downwards, so it will be negative, and the unit is decibel per decade. Okay, for both diagram and phase diagram, for magnitude of both diagram and phase for both diagram, we need to draw the diagram using a log graph. Okay, so in the log graph we know that a decade is value from here until here, 1 decade equivalent to 10. Okay, so this is 1 decade, 1 decade, 1 decade. So that's why the unit for the slope of this diagram is called dB over decade, because it is measured decade by decade, same as the phase both diagram. Okay, so next we proceed to Nyquist plot. Okay, what is a Nyquist plot? A Nyquist plot is a parametric plot of a frequency response used in an automatic control and signal processing. The most common use of Nyquist plot is for assessing the stability of a system with feedback. So our system RFID door lock consists of a feedback, which is the sensor we set at 1, the value of 1, and we can call our feedback as unity feedback with value 1. So we can use the Nyquist plot to determine the response used in automatic control to determine the stability of a system. Okay, so we just insert the same code as the both diagram into the Matlab command window by only change the command to Nyquist. Before this we get root R locus, and then we use both. Now we use Nyquist to generate the graph of Nyquist plot. Okay, and then we get this type of plot generated by Matlab. Also on the S-plane, we have the real axis for the x-axis and the imaginary axis for the y-axis. Okay, so as you can see, our Nyquist diagram, we have a stable. We can call this graph as stable because all the line is located on the left hand side of the plane. As you can see, the scale here, okay, the scale here is 0, or the origin is located here. So everything is plotted on the left hand side, so we can consider as the system is stable. Okay, that's all from me. Thank you very much. We proceed to the next subchapter.
So the next part is I'm going to introduce to you to PID controller. So the concept of PID controller is you put one transfer function before the plan in the block diagram. So by doing this, you're going to increase the rate of time to obtain steady state and reduce the amount of overshoot and also decrease the settling time. So we're going to use Ziegler-Nichols rules for tuning the PID controller. So there are PID, which is P is proportional, I is integral, and D is derivative. So from the PID controller, we're going to compare the effect of P, PD, and PID controller by tuning each other. So for P controller, which is proportional control, so we're going to use Simulink to operate this section. So as you can see from the figure below, that is how we find for P controller. So the first step is we put 1 on the proportional, which is P, and then next one is we're going to compare it with PID, which is we insert 1 for proportional and 0 for integral and 0 for derivative. So the next, this is the graph after we put 1 on the proportional. So as you can see from the graph, so this is the initial graph that we obtained from the Simulink before. So after we put 1 on the proportional, we're going to get this graph. So the advantages of PID controller is it decrease the settling time, and also decrease the amount of overshoot, and also increase the steady state. So we're going to tune by using the Ziegler-Nichols rules. So lastly, we're going to get the value of the proportional, which is, as you can see from the figure below, it shows that the value of P is 9.8399. So that is the amount of proportional that we get after we insert 1 on the proportional. So after we tune, we're going to get the graph, as you can see from the figure below. That is the graph after we input the P as 1 on the P controller, and this is the last result. So that's all from me. Thank you.
Okay, so the proportional and derivative control PD, we still use the same block diagram as you can see in the display, and after we key into the Simulink, we will get the trend of the step response as shown below. This is before we apply the PD controller parameters. Okay, so as you can see, the trend shows that it has high overshoot and it has longer settling time. Okay, so before we tune the parameter of the PD, we will need to apply an initial setting of PD, which is the P we put 1 and derivative D we put 0. So we tune it several times until we get the optimum parameters. So after we got the optimum parameters, we will have the trend of the set response like displayed now, and as you can see that the trend now has low overshoot and shorter settling time. Okay, so the setting that we have tuned for the parameter is shown on the display now, which is the proportional is equal to 2.728 and so on, and the derivative d is equal to 0.090 and so on. Okay, so this is the value of the we tune it until the optimal PD parameters. Okay, so to see clearly what's happened or the trend is that you can compare the trend side by side. So as you can see that the dotted line is the untuned trend before we put on the PD parameter, and as you can see clearly that it is higher overshoot than the solid line. The solid line, by the way, is the tuned trend. So also you can see that the dotted line has longer settling time compared to the solid line. So it is concluded that the PD parameters will make the overshoot lower and settling time shorter. Okay, so that's all from me. Thank you.
Finally, we're introducing the PID controller into the system. So what is PID stands for? So P stands for proportional, I stands for integral, and D stands for derivative. So we are using the initial condition 1, 0, 0, which is 1 for proportional and 0 for both integral and derivative. So as we can see from the graph, the dotted line represent for the system before PID was introduced. Meanwhile, the solid line graph represent the system after PID was introduced. So the difference between these two graphs is actually the settling time. For the solid line graph is actually shorter than the dotted line graph, which is before the PID was introduced. The overshoot of the solid line graph is actually less than the dotted line graph. And then after the tuning process, these are the value for the proportional, integral, and derivative. So finally, we will move on to our conclusion and recommendation.
So we have reached the final part of our presentation, which is conclusion. So as a conclusion, we can say that our main objective of the project, which is to produce a more efficient way of locking and unlocking the door, is achieved. So we have determined the input and the output of the system. So from there, we're able to produce a transfer function, and we'll be able to analyze the system performance. From the transfer functions, we're able to analyze the board plot diagram, we can construct the root locus, and many more. Finally, we also have successfully applied the PID controller into the system. The function of the PID control system was to improve this overall system, such as to reduce the overshoot value and to improve the settling time. So for the recommendation for improvement, it will be presented by Wan Haikal.
Okay, now we have come to the very end subtopic for this project, which is the recommendation that we would like to suggest to improve the finding for our project. So there will be 3 recommendations that we can do to improve our result. That is, first, we need to improve our transfer function as to obtain more stable system. As we can see before, we get the root locus, which is not very stable because it located on the right side of the S-plane. So we think that we need to improve our transfer function by fix the derivation on getting the final transfer function for our project. So next, we need to be able to simplify complex equation in order to obtain the proper form so that we can manually plot the graph. We go back to the boat and Nyquist. We are not able to plot the graph manually because our transfer function was very complicated, very complex. So if we able to simplify more the transfer function, and then we think we can separate the transfer function into its constituent part, like the real pole, the real zero, into its constituent part, and then we can plot manually the both and the Nyquist plot. And the last recommendation is, basically we require more knowledge on Matlab regarding the coding to produce a detailed graph containing more information of the graph made. Okay, because Matlab is a very wide software that we need a number of knowledge regarding the coding that we need to insert into the command window. So if we know more coding, more knowledge about the coding, so then we can obtain a graph with more detail and information generate. So for our project, we only use the basic coding to get our root locus, our boat plot, and our Nyquist. So I think if we acquire more knowledge, if you know more about Matlab, okay, we can get a better graph that contain a lot of information, so we can use it for our result for this project. Okay, thank you. Assalamualaikum.